when I set this up. So. Okay, so what we are doing today, our entire focus today is essentially finishing out chapter 8. I know there's some other stuff in chapter 8, but this takes us through the problems that I assigned, and we can always come back to things like variational principle if we have time later. I'm kind of looking ahead and seeing where I can rearrange some of the topics. But today the focus is how can we use the self-adjoint ordinary differential equation, that form, to determine the eigenvalues. And remember that if these are self-adjoint, essentially we're looking at Hermitian operators, which means the eigenvalues are real, which means that they're observables and all of that stuff. So that's why we want to do this. The applications, as last time, there are many. And some of them are obvious and some of them aren't. Today we're going to look at the Legendre equation, which we've seen, I don't know how many times before in your homework. So we're essentially doing 8.3.1 from your homework. So as long as you kind of follow along and then turn in your notes from today, that'll count for 10 out of 10 on that homework problem. The other problem in chapter 8, 8.3.4, does the same thing, but for the Legendre equation. So different solution, typically for something like the Laplace or the diffusion equation. So anyway, what we're going to do first off is start with the form of the Legendre equation. So what I've done is written it in operator form. So with the self-adjoint operator, L acting on Y is, oh, I missed a term here. It should be Y double prime. We've got minus times the quantity 1 minus x squared, y double prime, plus 2xy prime, minus lambda, which is going to be our eigenvalue, times y of x, since we're setting that equal to 0. Now, you might remember from E&M that in actuality, x is defined as cosine theta. This comes from separation of variables, and this is the theta term from that. So x has a value between 1 and minus 1. And in fact, and you can see from the form of C.1 that there are two singularities or singular points, that is x equals 1 and x equals minus 1. And those are going to come into play because one of the things that we're doing is we're going to develop, using the Frobenius method, a series solution. And then the issue is, does that series solution converge? Right? And if you've looked at what your book says, in fact, the series solution does not converge at the endpoints. And so one of the things that comes out of this whole development of series solution for ordinary differential equations is that if they diverge at an endpoint, then the eigenvalue problem actually shows us where we can cut off the series. It diverges because this is an infinite series. If we can somehow terminate the series, right, then we can make this series convergent over the region. And that's where the eigenvalue comes from. So that's our job. And our first step then is to write out each of these terms using our method for Frobenius. So our first step is to let y be equal to the sum over j, right, of a sub j x to the s plus j. Right, so that we're basically multiplying x to the s times our power series. Right? And I realize that the book hops back and forth between using L's and N's and K's and all of that. Here we're using S, right? So that means that y prime right, is just the first derivative of that. It's the same sum, but now it's s plus j times aj x to the s plus j minus 1. And y double prime is just one more of these. S plus j times s plus j minus 1, aj times x to the s plus j minus 2. Okay, so now this should always be your first step when you're doing any kind of series solution, is to just start off and recognize, and this is going to be the same no matter what problem you're using, right? Your the values for y and y prime and y double prime are going to be the same. So that's the first step. Step 2 is to look at the different terms. Let's shrink this a little bit. All right, oops. We have one term up here, we have another term up here, and we have another term there. So the second order, the first order, and the 0th order terms. And what I've suggested in the past is to create a table, right? And so that's what, in order to get the indicial equation, right? And so that's what you're going to do when I put you into your breakout rooms. That's the first step in this in-class problem. You're going to take this differential equation, and I'll get you started, right? I mean, you'll want to write things like -1 or minus times 1 minus x squared y double prime of x is going to be equal to minus s plus j minus 1 times s plus j times aj x to the s plus j minus 2 plus s plus j minus 1 s plus j times a sub j times x plus j. All I've done was multiply that through our y double prime, right? Call that a. Then our b term is just going to be 2xy, right? And, or 2xy prime, right? And you can see that that would be, and these are including the sums, right? So it should really technically have this under a summation, right? So sum, and in this case, this is just s plus j aj times x to the s plus j, right? We're just multiplying 2 and adding another factor of x. And then c is our minus lambda of y times y of x. And so that'll be the sum minus the sum of lambda times a sub j times x to the j. So you have those three terms. And what you're going to do in your groups is make, I suggest, a table, but you don't have to make a table. I want you to expand each of these terms. So your goal is to expand A, B, and C out to x to the s plus 4. That'll become obvious after we get to the indicial equation and start looking at the recursion relation. That means you're going to have to take a lot of terms up here, so make sure you have a lot of room in your scratch paper or your paper that you're going to be using. And do that for each, for A, B, and C. Right? And then, so you're going to do that, then you're going to compare terms in order to get the indicial equation. So that's the very first goal is to get the IE. And you get the initial equation by looking for the lowest order of x raised to a power, right? So if you look at that, you'll be able to see, assuming as we usually do, that a sub 0 is not equal to 0. That'll give you your equation for s. Okay? Everybody understand what they're supposed to be doing? So I'm going to give you about 10 minutes. And when you're done in your groups, you can come out of the room. That way I'll know that you're done. And if you need to send a chat, you can send me a chat and I'll hop into that room. But right now, your goal is to write out all of those terms because you're going to need that later, and then try and get the indicial equation. Give me a thumbs up if you understand that, what you need to do.
Can you lift like the page a little bit up?
I'm sorry, say it again.
Can you like lift the scroll a bit up because I want to see.
Oh,
opposite way.
Like that?
Thank you.
Okay. Yeah, so in C.2, that's always going to be true for any Frobenius problem, right? We'll call this C.3, this collection of equations. Those are specific to this particular problem because we have different things multiplying y prime, y double prime, and y. Okay? I'm going to open up some rooms then. And you'll get started. All right. Okay, there you go. Let's give you about 10 minutes, 10 to 15 minutes. When you're done, pop out of the room or send me a note. Did you guys not get a room? Why am I here? All right. How about that? That's weird. Hang on a second. This is weird. Move to Rick. Move to you guys in room 4? Rick and Tom? How'd you guys do?
Good, I hope.
Okay.
Happens with that.
Sure.
Good work, team.
Oh, hey, there she is.
Just checking in. How you guys do?
Whoa.
Just finished?
Oh, Allie just left. Yeah, so how far were we supposed to get? We found the
Just
indicial
the
equation
just the indicial equation.
and the expansions.
Well, we'll come to that, yeah.
Okay,
But just mostly just trying to get what the two values of S are.
yeah, 1 and 0.
Yep.
Yeah.
All right.
Okay, cool.
Awesome.
Got it. Thanks.
Hey.
Hey. All right. Get out of here.
Okay.
Eventful in math methods.
You're back.
All right. Let me.
You wearing overalls, Willow?
It's like a little romper overall
thing.
Okay.
It's not like denim though. It's very comfy. It's 60 degrees here today.
Yeah, you don't have to reduce the fundamentals. Put the numbers.
Hey guys, how you doing?
Oh, hello.
All right, we're working through all the DA terms.
Oh,
Yeah, like
so
we-
all I wanted you to do right now is just get the indicial equation.
Oh, yeah, we
Okay.
did that a while ago.
Just do that. So go
Oh,
back to
sorry.
the main room. I think you've done. We'll go
Oops,
back and do
okay.
that other stuff in a minute.
Okay.
Okay.
Sorry.
All right. No, my fault for maybe not. Yeah. Go back to the main.
Oops.
Okay. May have needed to be a little more clear about what the goal was for that. People were doing lots more work than me. So I'll be right back.
Start kind of doing what we did in the homework and like pair them up and
Hey guys,
hello.
Yep.
how
Hey.
you doing?
Slow
I
but
just
steady.
finished the table.
Okay, so the only thing that I want you to do right now is just get the indicial equation. So if you've got that, join the room.
Oh.
If not, if you need more time, do you need more time to do that?
A little bit.
Okay,
Not
about
too
one
much.
more minute.
Okay.
Sure. Yeah.
All right.
Dude, I have not started working on my presentation. I'm still trying to get my boat to work. It's bad. It's real bad.
Is this for AdLab?
Yeah. I mean,
that was the other thing I meant to say. I'm canceling office hours today so I can watch AdLab stuff.
ooh.
You're welcome.
Can we come watch too?
Probably.
Yeah, you probably.
Probably, yeah.
As long as you have the link, right?
Right, and they've been distributing. I mean, I got the link. I'm sure if you ask somebody, you can get the link. Are we all back? Who are we missing?
Tom and Rick.
Oh yeah, they needed one more minute. All right.
I have a question, sort of regarding the problem on the homework.
Yes.
So with 5.9, you gave us the series solution, what it should look like, and it didn't have the x to the s term.
Yes, right.
If we had started with what that should have looked like with the x to the s term, could we have just decided that s equals 0 and then
Yes.
gotten to what you had done?
Yep.
Okay.
Mm-hmm.
How would we have made that decision?
So I mean, I guess what you get from that is if you create the indicial equation, you'd get an s equals 0 solution. Some of this is practice, is recognizing when you don't have to use Frobenius and when you have to.
Okay.
It's in general, if you don't have any pathologies in the equation that are immediately obvious, you can get away with just a general series solution. And those are easier to use. So that's what I usually go for first.
Gotcha.
Yeah. I'll make it clear, for example, on an exam, if you should be using that or not.
Okay.
Okay. Okay. I think we're all ready here. So, something I'm not sharing again. Okay. So what I wanted you to do in this round was just get the indicial equation, right? And some of you went a little farther, and that's fine. Where am I next? So, and I'm aware of the time here, but I knew that this would take longer, but that's fine. So what you should have done is take each term, right? So you have, zoom in on this a little bit. So you have your A term, which you can write as just going term by term, minus S minus 1, S A naught X to the S minus 2, plus S minus 1, S times A naught times X to the S. We're just going through the different values of J now. Minus S times S plus 1, A1, X to the S minus 1, plus S times S plus 1, A to the 1, X to the S plus 1. And you'll notice that these two terms start repeating each other. And in fact, what you'll have basically this skipping over of two powers of x, right? So now if we go to the a sub 2 term, we have minus s plus 1 times s plus 2, a sub 2 x to the s, plus the same coefficient, s plus 1, s plus 2, times x to the s plus 2, minus s plus 2, s plus 3, a sub 3, x to the s plus 1, plus the same thing, s plus 2, s plus 3, there should be an a3 here, a2 here, a3 x to the s plus 3, and then finally s plus 3 times s plus 4, a to the 4, x to the s plus 2, plus s plus 3, s plus 4, times a to the 4, x to the s plus 4. I know that's kind of messy, but hopefully that's what you got. For B, it's a little less messy. It's 2 times a naught times x to the s plus 2 times s plus 1 times a1 x to the s plus 1 plus 2 times s plus 2, a sub 2 times x to the s plus 2, plus 2 times s plus 3 times a sub 3 x to the s plus 3, plus 2 times s plus 4, a sub 4 x to the s plus 4. And that's as far as I wanted you to go there. Let me zoom this in a little bit. And then C is even easier. That's just minus lambda a naught xs minus lambda a1 xs plus 1 minus lambda a2 xs plus 2 minus lambda a3 xs plus 3 minus lambda a4 xs plus 4. Okay. So that, in a sense, is one way of doing this. And now what you could do is create your table. What I asked you to do is find in this section the indicial equation. And the way that you find that is to go for the lowest power of x, which is right over here. And since that's out on its own, there are no other powers of x to the minus 2. The coefficient of that has to be equal to 0. So minus s minus 1 times s times a naught has to be equal to 0. So that means that s is equal to 0 or 1. All right, so that's the roots of your indicial equation. Did everybody get that? Thumbs up if you did. Okay. Step 2 now, what I'd like you to do is we're going to look at s equals 0. So we're going to take these equations, which I'll call C.3, and I'll leave these up here, even though it's kind of messy. So the next step, I forgot what step we're on, step 3. No. So step 3, we're going to choose s equals 0. And what you're going to find with that is that a naught, we know, is not equal to 0, and a1 is going to need to be equal to 0. And what I want you to do is find solutions for a2 and a4 in terms of a naught. Okay? Sound doable?
Are we not caring about the other two terms of A, like the other two s plus 3, s plus 4 terms that we would get if we kept going?
For where?
If we kept going with A for a
Oh.
couple more times, we would get A5 x to the s plus 3.
Oh, right. So we're not. So right now, what we're setting up, and we may not have time to do this, is basically if we have enough terms, we can by induction create the recursion relation. Okay. Otherwise, we have to look at the full equation with indices, and I'll probably have that because of time of how you do that just from first principles. But what I'm trying to do here is if you get basically the first three terms, you should be able to, especially if you have a little bit of experience with this, use mathematical induction to find out what that recursion relation is. They're not, I mean, these, of course, these would keep going. But usually 3 terms is enough to figure out what the recursion relation is. So that's why we're stopping there. And we happen to know, since A1 is equal to 0, that this is going to be an even series. So we need to look at A0, A2, A4, because A1, 3, and 5 are going to be 0. That make sense?
I also have a question.
Sure.
The textbook talks about, they say something about like you should always use the higher number for the indicial equation, but I wasn't really clear on why they said that.
So what you're looking for, the highest value?
Well, yeah, like they say if you have s equals 0 and 1, you should always use 1, and that's like the regular solution. But they didn't really, I didn't see an explanation.
Yeah, that was for the special case with the regular points and irregular points. So here we're not dealing with any irregular points.
Okay.
Yeah. So in the case in that problem, I think it's the last problem in the homework. The regular point, and that's because of whether you're identifying p sub -1 or q sub -2, right? Okay, I'm going to send you to your rooms and get these relations. Okay, so right, can you, let's see, I have you in these rooms. Can you join back to your rooms? I've never done this before. Go
Yeah,
back to your rooms.
Yeah.
I don't want to mix these up again. How'd it go?
Good. We're slightly disagreeing on one thing, but rather than compare our work, we're just going to see who's right.
Okay, sure. And what I'm going to do is post a video with the complete solution. This is just to get you to see how this goes. And then basically, you won't have to do problem 8.3.1, but 8.3.4 is essentially the same, but a different differential equation. All right, I'm going to start closing all the rooms now. Okay, sorry I had to cut that off. We're running out of time. I'll go over the solutions, and then I'm going to upload a video that goes through the whole problem. You won't have to do 8.3.1, but 8.3.4 will follow the same idea. So what you should have found was that A2 is equal to minus lambda over 2 times A naught. Thumbs up? All right. And then A4 is equal to 6 minus lambda over 12 times A2. And if you wanted to write that in terms of A naught, that would be minus lambda times 6 minus lambda over 24 times A naught. Now, the reason why you would want to write this in terms of A naught is that then this allows you to write the series expansion. If you look at the question, 8.3.1, part B, I think, is writing this expansion. What's really useful, though, is are these two things, because either from mathematical induction or by doing the full problem that is looking at just general J's and S's, you can create a recursion relation. And I'll do this in detail on a supplemental video, but what you would find is that A sub j plus 2 is equal to j times j plus 1 minus lambda over j plus 2 times j plus 1 times A sub j. 2.4. So that's the recursion relation for even numbered, that is for the s equals 0 case. And if you put in j equals 2 or j equals 0, you should be able to see that you get the 2 of the 4 terms. Now the problem here, and the whole point that this lecture was leading to, is that if you test this series for convergence on the endpoints at x equals 1 or minus 1, they diverge. And in fact, this is a case, in fact, it goes back to the first problem set where you have to use the Gauss's test to show that this is divergent. To avoid that divergence, then, you have to terminate the series. And the way you do this is you terminate the series at some j equal to L, such that lambda is equal to L times L plus 1. Right? And you can see that if that's the case, right? If you substitute in, this is C.5. If you substitute in those values, then you would have L times L plus 1 minus L times L plus 1 over L plus 2 over L plus 1 equals 0. And so the series terminates at A sub L. Now, because of the way we've constructed these series, these are even values for J, and because S is equal to 0, that means that our solution, our Y of X, is equal to the sum of A sub J X to the J over even values. Where we can actually normalize these things. This becomes then the even powers of the Legendre polynomials. If you think back to E and M, right, the Legendre polynomials, if you have normalized them correctly, first one is 1, the next one is minus x, the next one is x squared minus 3 halves, right? So if you think about p sub 0, that's an even one, p sub 2 is another even one. You get the odd series from choosing the s equals 1 solution and then terminating that. And when you terminate that, your x is going to be at, excuse me, your terminal power of x is going to be L, some even number, L plus 1. In other words, it'll be odd powers of x. So I'm going to write this out in general, but the idea behind this entire exercise was to look at the indicial equation, make a solution, and then notice what we've done, sort of hidden in behind this, is that we took this lambda, which we knew ahead of time by definition and construction is what we're calling our eigenvalue, and we placed a restriction on it. Our restriction then is that lambda is equal to L times L plus 1, where L is an integer. So that means that this lambda represents the orbital angular momentum quantization in Schrodinger's equation for the spherically symmetric Schrodinger equation. By terminating that series, we were able to not only identify what the eigenvalue is, but show that it is quantized and that we can identify, you know, the orbital angular momentum numbers and the total orbital angular momentum in terms of this L times L plus 1, which is pretty cool. So we were able to do this just from the standpoint of taking essentially Schrodinger's equation, separating variables, which we'll do on Friday, looking at one particular piece of it, and then knowing that we need to terminate it in order to have a convergent series, we're able to identify what that lambda is and find out that lambda isn't any old number, it's actually a discrete set of numbers, quantized numbers, which makes sense since we're dealing with the Schrodinger equation. All right. How does everybody feel about that? Need a little more practice with it? This is cool stuff, but it's also kind of tricky. So I'm going to let you go. We're way over. I'm going to upload a video that shows how you do this in general and how you do the odd series as well. So take a look at that. And then again, for those who didn't hear, I'm not going to have office hours today because I want to watch the ad lab presentations. But I'll have my normal office hours the rest of the week. Okay, if you have any questions, ping me and I'll jump on and talk to you or just answer email. Okay? All right. See you guys.
Bye, thanks. Bye,
Bye.
Allie. Bye, Meg.